Hi everyone, what's up? We want to pick up where we left in the previous video. The goal we had was to fine-tune a FLAN T5 model for sentiment analysis of financial tweets and news headlines. So we saw that FLAN T5 is a Google model, is a LLM which comes in different sizes, and it starts at 80 million with FLAN T5 small up to 11 billion parameters at T5 XX large. And here you see their performance in different benchmarks, comparing it to different other models, and you see here 52.4% on average is pretty comparable and amazing compared to other models of 120 or 175 billion parameters. So FLAN T5 has a good potential. We used the model the other time. We ran it on different types of questions and we checked different sizes, even quantized models. But one of the challenges with FLAN T5 is that you really want to fine-tune it to your specific application or instruction before being able to use it efficiently. For my case here, I'm going to use FLAN T5 base with 250 million parameters. This is a pretty small model and you see the scores are not that good. We will run some fine-tuning and try to improve the performance based on few shot training. Here is the homepage or the Hugging Face page for this model. You can find some information here. You see this is a pretty common model for usage. We have 14 quantized versions, so people have already quantized this to 4 bits and 8 bits. There's also a lot of fine tunings, and honestly I found interesting ones here. You see we have one for hallucination evaluation model. So this is where you can use one model to detect hallucinations of another one. Pretty interesting use case. I believe I found one that was trained for coding. You can have trading candles and many other use cases. This is pretty interesting page. I do recommend you check it. You try to use some of them and see what's the performance before and after this fine-tuning. Another article I wanted to show you is here. This is a comparison of FLAN T5 with Llama. This is a pretty recent article. The discussions are very interesting. Something that I found interesting to me is the information that they provide based on the prices, the cost, and also the performance optimization. For example, they ran the model on Google Cloud Platform, and based on their analysis, NVIDIA L4 GPU is the one that's most cost effective. They have interesting discussions and analysis on this page, and here, for example, this is what I understood from their analysis, that there are businesses that don't have or don't want to spend hundreds of thousands of dollars for AI application in their domain. So for them, for example, for internal document summarization, classification tasks, or whatever task where the accuracy is not key, so something around 80% or even below could be acceptable. A FLAN T5 base or a bit larger models could be a good solution. And in the end, here's the summary. For high volume, low complexity tasks, FLAN T5 is a model that could be the best cost-effective choice. But for applications where you want to have advanced creative or generative usage of AI, then you would want to go for bigger models and more advanced structures like Llama 3. And again, for research and development, this is the use case where you want to modify the model, test again and again, and do a lot of inference, training, fine-tuning. This is where you want to be fast and you want to be efficient in terms of usage of the resources. So this is again a place where FLAN T5 could be an interesting solution. Now let's go to the code. So I've already prepared this notebook and I ran all the code. We will see the results step by step. First of all, we import the libraries that we need. We need transformers library, the model class, the tokenizer class, and also the trainer and its arguments. From the PEFT, which is parameter efficient fine-tuning library, we need the model, the task type, and the config and get model. Datasets is the library that we use for importing datasets for our training and inference. So here I define my model. It is located at saved models folder locally, here in the base folder. Then here this is a function that gets a model and returns the number of parameters and the percentage of the parameters that are trainable. This is my original model and original tokenizer. So it's good to mention that tokenizer doesn't change. We don't change the tokens, we just change the model and add some parameters to this during fine-tuning. And here you see I'm passing this model to the trainable parameters function, and you see we have around 248 million parameters, out of which 248 million, 100% are trainable. So this is the original training method or the technique that we use for full parameter fine-tuning during the original training of the model, and then again for fine-tuning if you want to train all the parameters. Here you see we have the forward path in blue and the backward path in green, and for one loop of training you have the input which is fed to the model, then you infer the output. Based on the calculations and the target that you had, you will calculate the error. Then you do the back propagation where you will determine the gradients and make adjustments to your weights here. So based on the number of parameters and the number of loops that you have to train, you are going to need a lot of resources, and it's going to take a lot of time to do this kind of training. So this is already done initially by Google for this FLAN T5 model, but now that we have this model, we don't want to redo the whole thing like this. Instead, we have the LoRA, which is Low Rank Adapters, which is another technique for fine-tuning that is more efficient in terms of resources and time for fine-tuning a model. So in this case, we have again the same model, but just look at it. We don't have any backward path going through this model, which means we are going to freeze this model and all of its parameters, so this model doesn't change. Instead, in parallel, we add another loop. So here we do have also a forward path and a backward path, and here in this we have some low rank matrices which are added to add some flexibility and the capability of learning to the model. Basically, these matrices are much smaller compared to the number of parameters that we have here, and this is why the LoRA fine-tuning is faster. So here I'm defining my LoRA configuration because I want to infer a parameter efficient fine-tunable model from it. So the task type is the same task type as the original model. Then the R is a ratio or a scale of the size of these matrices. So the bigger the R, the more parameters you are going to have, the bigger the learning capability, but again you are going to need more resources for training. LoRA alpha is a scale of how fast your model or how large the impact of these matrices are going to be, and usually the ratio of LoRA alpha to R is the learning speed of your additional loop that you have here. I'm adding 5% dropout because I don't want to do overfitting, and our target modules are the attention masks and the query and value modules. So here with the get PEFT model, I pass the original model and the LoRA configurations. It will return a model which is fine-tunable. And when you print the parameters of this model, you see that we have some additional parameters. Before we had 247.6 and now we have 248.7 million parameters. So around 1.1 million parameters were added, which are trainable, and the rest are freeze. So the trainable percentage is 0.44, which means we are going to train only a tiny fraction of the parameters of the model. Here is my dataset. I have a dataset extracted from this zero shot page. This is a Twitter of financial news and its sentiment analysis output. We have 0, 1 and 2 for negative, positive and neutral sentiment, and Here you see the text and the label. You see some of them include URLs which are not useful for us. I'm going to remove them. And one more thing that's important here is that you would want to pay attention to the balance in your dataset. So here only 15% are negative, 20% are positive, and 64% are neutral. So when trying to assess the performance of our model, we need to pay attention to this. Now let's come back here. So you see we have around 9.5 thousand lines or records here. I've already added the instructions to these lines. You see instruction is what is the sentiment. Choose one from the list, negative, neutral, or positive, and then I added this tweet text. And the field or the key called target is the label that we already have inferred. So this is a data set, and here what I'm doing is that I'm loading this using the load dataset function. Then I have a clean function defined here that is splitting the text of the context by HTTP, and I'm taking whatever is before this HTTP. So basically I'm removing whatever URL that might exist in the text. And then I'm mapping this function to all the cells of this dataset. Then I want to have 10% left for testing and validation. I'm going to use 90% for training. Here you see the structure of the dataset. We have train and test as you saw before, and the context and target here 8.6 thousand rows for training and 955 rows for testing and validation. You would also need a data collator function. This function is going to get 4 lines here of this data, and what it needs to do is to return the tokenized version of the context and the target. So it's going to get 4 lines because well, here it's 8, but originally I run everything with 4 and 4. So the batch size is 4, which means each time this data collator function is going to receive 4 lines of data here, and what it needs to do is to tokenize the input and return PyTorch tensors. And also in the end we are going to add another column which is called labels, which is a tokenized version of the target. Now we can go for training. Before launching the training, I'm going to define the training arguments. I want the logging to be in this folder. I want to log every 10 steps now because I want to see the results quickly. This is the development phase. In normal case you would want to have 100 or 200 logging steps. Then I want to have 3 epochs for training. I have 4 lines per each training batch, and each 4 batch of training I want to do the accumulation of the gradients and adjustments of the weights. The other important parameter is the learning rate. I put it to 1e-4, and I have 200 warm-up steps. So this warm-up step means that you will start your learning rate at 0, and then during 200 steps your learning rate is going to increase linearly until it reaches your target, which is in our case 1e-4. And then we have a weight decay, which means the learning rate will stay here for some time, and when it's reaching the saturation of learning, we are going to decrease the learning rate exponentially back to 0, which means we have already trained the model enough. Now we just want to do very small fine-tunings of parameters, and the learning rate is going to 0 because of this. So this article compares the performance of their model with and without this kind of weight decay. And you see with the weight decay you have a lot of volatility in the beginning, but then when your model reaches a stable situation, the performance is better than a model without the decay. And here is the performance: 89% accuracy compared to 86. Let's go back to the code. So another parameter that's active here is the floating point 16, which is not useful here because I'm running on CPU, but if you have a GPU there are several parameters like this one. I can deactivate this but in this page you will get a list of parameters that you can optimize based on the GPU and the system that you're using to run this training. Alright, so here to this trainer class I'm passing the model, the arguments, and also additional information needed. Now we can run the training process. Well, before running this, I would want to reduce the number of logging steps so we could see some steps and how the loss will change. So you see now it's running. We have the progress displayed here, and the estimated time to finish is around 1 hour 40 minutes. Now step 10 is going to finish and we are going to have one logging step. Okay, I will stop it here. We have this step 10, the training loss is 1.54, and you see the learning rate is 4 to E-6, so it's far from what I've set for the final value, and you see this is the linear increase that I was talking about. And I wanted also to monitor the CPU usage, so I run it again. So you see the processor is significantly loaded, but still we have a lot of margin before we reach full CPU usage. One way to increase the CPU usage is perhaps to increase this number of batches, and also I will have to reduce the number of accumulation steps to keep 16 samples. So I'll stop it here again now and run it with the new settings. Well, the estimation time didn't change that much. Memory usage is normal, and the CPU usage also seems to be the same as before. Okay, the loss has decreased already, so we had a bit of training here. Well, I'm going to stop this because it takes a long time to finish, but I finished this before, so we have the results of the full fine-tuning. So the next step after finishing this fine-tuning is to save the model. We use the same method as always, save pre-trained, and the model is going to be saved in this folder. You see it here. I'll save it again. So this is a fine-tuned model, and as I explained before, we are going to have the adapter which shows the settings of our fine-tuning. This is the original model, and then also other settings that we had, in addition to the tensors and the values that we tuned. So now this is done. I've already fine-tuned fully, and I stored the model in this folder, fully fine-tuned. Now we want to compare the performance of our new fine-tuned model against the original model to see what was the performance increase. And here I'm loading again the base model, which is going to be the original model without any fine-tuning, the zero-shot model. I'm defining X and Y as the context and target of the dataset, the test dataset that we defined before. And here I just ran a test for X, the 11th element. You see already a difference between the two models. The base model is predicting negative. And here I'm defining the PEFT model from pre-trained I'm passing a deep copy of the base model and also passing the address to the fine-tuned files. So this is the method from the PEFT library that can load a PEFT or a LoRA based fine-tuned model. Here I'm doing a deep copy of the base model because this function will change the model that you give to it as the original model. So I wanted to keep the base model untouched. That's why I'm passing a copy of it in the memory and then also this fully fine-tuned folder. Okay, now let's run the comparison. So what I'm doing is that I'm defining two functions. One is predicting base model and the other is predicting PEFT model. I'm tokenizing the input, then I'm asking the model to generate the output and then decoding the output tokens into real sentences and returning it. Here I'm measuring the time, and n is the number of the inferences or the elements in our test dataset. So I'm defining the inference speed or the time that it takes to process each sample, and the accuracy also I'm calculating it myself. We could use the sklearn tools too. Same for the PEFT model, and here you see the result. So the inference speed is more or less the same, it's not that different, but the accuracy you see a big increase. Well, I'm quite happy with the accuracy increase here, given that I trained a model with only 250 million parameters and on CPU for less than 2 hours. This is a pretty good increase in performance. But let's not forget, our dataset here was not balanced, so accuracy alone is not a good metric for performance. So here I'm using the confusion metrics from the sklearn metrics library, and this first one is the confusion matrix for the base model and the next one is for the PEFT model. Here the columns are the predictions and the rows are the true values. So true negative before fine-tuning the base model was able to detect 99%. And it was a very high level of accuracy. For neutral the accuracy was 0 and for positive the accuracy was 54%. And one thing that you can obviously see is that the base model is never detecting anything as neutral. It's always categorizing the inputs as negative or positive. And here if you compare this to our new model's performance, you see that the neutral is pretty accurate, 89%, 72% good improvement for the positive detection, but compare this to 99% accuracy. We have a big drop in predicting the negative sentiment, and this could be due to overfitting. This could be due to the hyperparameters that we have. So whatever it is perhaps something that we can improve. We just need to play with our parameters or also increase the number of epochs and then see what we get. So now that you have your fine-tuned model, you don't always want to use it with the PEFT library. The solution is to load this as a PEFT library once and then call the merge and unload method. This method will merge the two models, so it will implement the additional parameters that we had here. So it will take these matrices and implement them in a bigger unified model. And then as the normal model here we can save them, and if you check in the merge model now, I'll run this. Well, I have to define, so I need to run these codes. Alright, and now I can run this part again. So I corrected this address. This was the problem that we had in the code. Now what it does is going to save this model to this address, and then we are going to load it with a pipeline. So now that we're loading this model, we are not using any PEFT library, or we are not pointing to an original model or using the fine-tuned matrices. If you check this merge model folder, you have the config.json, generation config, and model safe tensors. This is pretty similar to what we expect in a normal model. Well, it does not include the tokenizer files. You can copy them here, or when we are loading it, we can define the tokenizer like this. Alright, so the model seems to work. What I did also was to check the performance of this model. Well, the accuracy is the same, the confusion matrix is the same. The only thing is that the speed is a bit lower. So instead of 161 or 171 milliseconds per sample, here we have around 20% increase, and we have around 215 milliseconds per sample. So this is a bit slower. This is why I loaded this again with T5 for conditional generation. So here I'm loading this again, and the same performance evaluation. You see the accuracy is again the same. Nothing has changed, but the speed is much better than before. So this model, a unified T5 for conditional generation class model, is much faster than the pipeline and also the PEFT from pre-trained class. The confusion matrix, of course, is going to be the same. So in the end, I did also compare the X-large, large, and X-large quantized models with the same test dataset, and you can see the X-large model with 3 billion parameters, the accuracy is 66%, except that it takes 1.47 seconds for the normal model, or for the quantized. In my case, I have a CPU, so it's slower compared to the base model. And here you see the magic of LoRA fine-tuning. With only 248 million parameters, we have an accuracy of 81 or 83 based on how much you fine-tune the model, and it can run quite fast on the CPU. I hope I've clearly shown what is the LoRA and the PEFT libraries application in fine-tuning, and how we can do that, and how efficient it is for specific use cases. See you next time.